Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to one of the coolest methods to evaluating limits prior to the actual rigorous, precise definition of evaluating limits. This method is going to be used continuously by you as you go through limits, so it's good to pay attention to all the ideas presented here. And we don't have a lot of examples because you don't need a ton to kind of get the point. Now I'm going to start this video with a mantra that I state to a lot of my students. It's very important that you do mathematics in the order that you learned mathematics. That is, you perform arithmetic before you perform algebra. You perform algebra before you perform trig, and you perform trig before you perform calculus. Notice the very last thing you should do in any problem is perform calculus. And this is just a fancy way, or maybe a non-fancy way of saying you need to do all your prerequisite skills before you start doing your calculus skills. That's why prereqs are so important as you head into calculus. If you have shaky algebra skills, it's going to be very tough for you in calculus because there is no reason why you should have bad algebra skills in calculus. Everything you've done in algebra is needed in calculus. So let's start this first example with that in mind. Evaluate the limit if it exists. If it does not exist, please explain why. In the previous video, we learned of something called direct substitution, and you're allowed to use direct substitution on polynomials and rationals, polynomial functions and rational functions. That is, if the value that x is approaching is in the domain of your polynomial or your rational function that you're looking at, you could directly substitute that in. So the first thing I'm going to look for is, can I just plug in a -2 into this rational function? Honestly, all I'm concerned about initially is, can I plug it into the denominator here? Because polynomials, their domains are all real numbers. And so in the numerator, I can plug in -2 all day long. The only thing that I have to be concerned with a rational function is, does that denominator become 0? I'm gonna scoot over to the side here just to give myself a little more room. And you can see that denominator definitely becomes 0. There's no point in me continuing forward trying to use direct substitution. I know direct substitution will not work. However, I am going to actually plug that -2 into the numerator for a very specific reason. Notice that numerator also will tend to 0. So this is a situation where our rational function is tending to 0 over 0. So I go back to that mantra. I'm going to perform arithmetic before I perform algebra, algebra before I perform trig, and trig before I perform calculus. By the way, if you have a college where your algebra sequence goes like this, or maybe your math sequence goes like this: arithmetic, pre-algebra, elementary algebra, intermediate algebra, trig with college algebra, pre-calculus, and then calculus, which is how we do it at our college, really the statement about arithmetic stays here. Then algebra, that contains pre-algebra, algebra 1, algebra 2, college algebra, and pre-calculus, really. That's all the algebra from all those topics. Then trig is obviously just trig. Then finally you get to do calculus. So in this case, with the function within this limit, there's no arithmetic you can do, but there definitely is some algebra. You can factor here. And this is why the prereqs from your algebra, which is specifically your college algebra or your pre-calculus, is so important. In your college algebra or your pre-calculus, you learned about the factor theorem, the remainder and the factor theorem actually. And one thing that the factor theorem told you is that if you plug in a value of, let's say in this case, a -2 into your polynomial, we're just going to focus on the numerator for right now, and the numerator becomes 0, that means that x minus that -2 is a factor. Same thing in the denominator. If you plug in a number into the function in the denominator and that forces the denominator to become 0, then x minus that number you plugged in must be a factor. So recognizing that should be automatic for you. You have had that skill in a prerequisites course, so it is assumed you know how to use that skill. If you do not, I will link into this video my review video on the remainder, factor theorem, synthetic division, and whatnot. Knowing that I can factor out x minus a -2 out of both numerator and denominator is very helpful. I'm going to go ahead and use synthetic division to go and do the division to find out what the quotient is. Dividing by x minus a -2 means that I'm going to do synthetic division by a -2, and that will, after using synthetic division on both numerator and denominator, yield the coefficients of the remaining polynomial, which is called the quotient, after dividing by x plus 2. So let's see, the leading coefficient of x to the 5th is that 1. The leading coefficient of x to the 4th in the numerator is 0. The leading coefficient of x to the 3rd in the numerator is a -8, and then a -6 for x squared, +7 for x, and then a +6, which is supposed to be positive. My pen kind of got a little bit messy there. +6 for the constant. Now I'm going to go ahead and bring down the 1, multiply 1 times a -2, and put it right there. Add 0 to -2, multiply -2 by -2, add down, multiply -2 by -4, add down, multiply -2 by 2, add down, multiply -2 by 3, and add down. We knew that that remainder, because that's exactly what that last digit represents, is the numerator of the remainder. We knew that was going to be 0, so this is no big surprise. But what's important here is that we now have the leading or the coefficients of each term in the remaining polynomial. So when I divide that numerator, x to the 5th minus 8x cubed minus 6x squared plus 7x plus 6, by x minus a -2, I get the following. X minus a -2, which is x plus 2, times the quantity 1x to the 4th minus 2x to the 3rd minus 4x to the 2nd plus 2x plus 3. You can see where I'm stealing these numbers from, hopefully. 1, -2, -4, 2, and 3. Now we're going to go ahead and do the same thing for the polynomial in the denominator. Again, we're dividing out x plus 2, which is x minus a -2. So we'll do synthetic division by a -2. I wrote down the coefficients of each of the terms in that denominator, 2, -1, -8, and 4. You bring down the 2. 2 times the -2 gives me -4. You add those two together, you get -5. -2 times -5, +10. You add those two together, you get a 2. -2 times 2 is -4. You add those two together, you get 0. And that should be no big surprise because that's the numerator of the remainder. And we know the remainder should have been 0 because, again, when you plug -2 in, we got that the value turned into 0. So the value is the remainder by the remainder theorem from your prerequisite algebra course. So now we know the way it factors in the denominator is x plus 2 times 2x squared minus 5x plus 2. Now we do all this so that we can cancel those like factors in this function. Now, before I go any further, I don't want to have to do all that factoring again. So I'm going to go ahead and do algebra, a little bit of earlier algebra before I do that high level factoring algebra. If I don't have to do it, then that'll be awesome. So let's go ahead and see if we can just plug -2 into both the numerator and the denominator. And as I did last time, I'm going to start with the denominator. And we are in luck. That denominator does not tend to 0, so I know that I can just use direct substitution here. Now I'm going to go ahead and use a little bit more rigor in this. Actually, this is pretty rigorous already, but I just want to showcase kind of the thought process and what you need to do symbolically to showcase what you're doing. Notice I did all my algebra on the side here without limit notation, and that is okay. Most instructors should be fine with that. What you don't want to do is you don't want to just drop your limit notation, this notation right here, and never mention it again. Because the reality is x is approaching -2. It's not becoming a -2, it's approaching a -2. And so you need to use limit notation as often as possible or as often as justified. So the next step in line, what I would do if I was a student, is I would go ahead and rewrite that limit without those x plus 2's because they canceled beautifully. And then I would say this equals, and above that I put this notation, d.s. That means direct substitution. And I'm using direct substitution because, well, the denominator does not turn into 0. This allows me to just plug in -2. So as x is approaching -2, that denominator will approach something non-zero. Via direct substitution, we already actually computed the denominator. It's 8 plus 10 plus 2, which is 20. The numerator is going to take a little extra work, so I'll go ahead and take my time with that. And finally, we get to this. And 3/4 is what that limit, the original limit, will be. Now note what I did at the end there. Not only did I tell the reader that I'm using direct substitution, not only did I evaluate that limit and do my arithmetic, but I also did my arithmetic even further by reducing this fraction down to a 3/4. Please make sure that you perform all your prerequisite skills while in calculus. There are some exceptions. If you have numbers that are ridiculous, like a 3-digit number over a 5-digit number or some silliness like that, then okay, that's understandable. But numbers this small, you should be able to reduce pretty quickly. Before we leave this problem, I just want to mention you always start the problem by just making sure that if you can or cannot use direct substitution. We found out very quickly we couldn't use direct substitution because that denominator tended to 0. Once I found out that the denominator was tending to 0, I went ahead and because the numerator is a polynomial, I did direct substitution on the numerator. And the reason why is because if that also tended to 0, that means that x minus the -2 would be a factor, which it is. Then I used synthetic division to find out how things factored, which allowed me to cancel the x plus 2 factors. I rewrote the limit, and then again I tried direct substitution. I used my arithmetic to clean things up in the end. And remember, it's always arithmetic before algebra, algebra before trig, and trig before calculus. As I mentioned at the beginning of this video is going to be somewhat short because you don't need a ton of examples to know that you just are going to have to rely on all of your prerequisite algebra skills. This type of problem is incredibly popular within calculus. Evaluate the limit if it exists. If it does not exist, explain why. The very first thing I'm going to try is direct substitution. Now, I'm not going to write it out. I'm just going to say that as x approaches 1, we know that this denominator approaches 0. So immediately I know, all right, direct substitution is not going to work. I'm going to have to do some algebraic manipulation. By the way, had you tried to plug in x equals 1 into the numerator, that would also have tended to 0. That's kind of important to note because if the numerator tended to something other than 0, let's say 5, then you'd have basically 5 over 0. And now we can start conceptually investigating this and seeing if it tends to positive or negative infinity. In fact, maybe I'll do a side example at the end to showcase that. But for now, as written, I know that this has an issue at the limit at x equals 1. So what do? Well, I rewrite the limit And then I need to do an algebraic manipulation here. The algebraic manipulation that I can do, the only one that I can do here, is conjugate multiplication. This is something that I tell my pre-calculus students right at the beginning of the course, and my college algebra students, that you are going to have to know how to multiply by conjugates to rationalize numerators or denominators in calculus quite often. You just have to do it. So I'll grab that entire numerator, and I'll grab that entire denominator, and I'll multiply by the conjugate of the numerator. As I tell my college algebra and pre-calculus students, you only need to multiply out or distribute through the conjugate factors, this stuff right here. You're going to multiply that stuff out. You will not multiply out that denominator. The only reason why you're multiplying this fraction by the conjugate of the numerator is so that that numerator can clean up. You do not want to multiply out the denominator because you need that factored the way it is. I'll showcase why. So multiplying out that numerator, those conjugates, I get x plus 3 minus 4. Cleaning that up, remember now that I've done a little bit of algebra, I'm going to go ahead and go backwards because I see that there's some arithmetic that I can do. And now that I've done my arithmetic, I see there's a little bit of algebra I can do because we have x minus 1 over x minus 1. Those cancel beautifully. That simple conjugate multiplication allows us to now look at this statement and ask, can I just plug 1 in here? And the answer to that is yes. The denominator is not suffering from that division by 0 issue, and so I now know that I can just do a little bit of arithmetic here to get the following. So this limit that we were asked to evaluate, which started as 0 over 0, is actually just 1/4. So again, all your algebra skills are going to be put to use when you are in calculus. Now I did say that I wanted to try out a different version of this. So let's go ahead and modify our limit. Let's suppose, and I'll go ahead and put a little bar here. Let's suppose the original limit was this. So you're at an exam or something like that, and you're asked to evaluate this limit. The first thing you should do is try direct substitution. You'll see that this denominator is tending to 0, but the numerator actually is not. If you were to allow x to be 1 here, you get the square root of 9 minus 2, or in other words, 3 minus 2, which is 1. And this you can evaluate somewhat conceptually. The problem here is that x is approaching 1 from either side, and so this 0 is either plus or minus 0. If you don't know that notation, go back to one of my previous videos in this calculus video series where I talk about evaluating or investigating limits conceptually. But in this case right here, if x were greater than 1, which is not guaranteed to be greater than 1, somebody didn't tell us that, but if x were to start as being greater than 1, then this denominator would be like 1.01 minus 1, which is close to 0, but it would be positive. And in that case, you would have 1 over 0 positive, and you know that's going to be positive infinity, because a finite number over basically 0, but from the positive side, let's say it's a positive finite number, that's going to be positive infinity. If it was a negative finite number over 0, again, but from the positive side, it would be negative infinity. But it's not negative finite. However, we also have the possibility that x was approaching 1 from below. And if x is approaching 1 from below, that is 0.99 minus 1, essentially, which is a negative side of 0, which means that we have a finite number over 0, but 0 negative. And that means that we have a negative infinity. So the value of this limit depends on which side of 1 x is approaching. And since nobody told us which side of 1 x was approaching, this limit is not going to exist. Now, that's not how you're going to write that if it were an exam or something like that. You would just see that that is going to be an issue, and you want to justify why your answer is DNE. You're going to say the limit as x approaches 1 from above, of the square root of 8 plus x minus 2 divided by x minus 1 has the following quality. This numerator is approaching 1. The denominator is approaching 0, but from above, and therefore this limit is positive infinity. On the other hand, if we look at x approaching 1 from the other side, that numerator is approaching 1, not a big deal. That denominator, though, is approaching 0, but again, from the negative side of 0, and so therefore the left-hand limit is negative infinity. And we have a theorem from the past. If the left and right-hand limits are not the same, then the overall limit does not exist. So that's a good example of what you would do if you were given a limit where the numerator was non-zero but a finite number, but the denominator was tending to 0. You break it into two cases to see if the left and right hand limits are the same. If they're the same, then that's the limit, the overall limit, that is. If they're different, then the overall limit does not exist. All right, so this is just what we needed to go through for this video. Just note that you're going to do things like clean up, compound rational expressions. You're going to multiply by conjugates. You're going to do a lot of factoring. All of that is prerequisite for this course, so you should be okay doing that. All right, I hope this wasn't too terrible. I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.